So my name is Brennan Bellinger, and I'm the group leader for the refrigeration experiment that our team is going to do next week. I guess we'll continue the theme of refrigeration. I think this is the third time you all have seen this, so it's probably a little repetitive, but I'll try to keep it interesting. So to start off, these are some of the things you can expect from this PowerPoint. I'm going to talk about the thermodynamic theory, so I go into what the refrigeration cycle is, its components, and what you can do with those things and why they're important. And also the goals of the experiment. So we're going to look at calculating the coefficient of performance. And I'll explain what that is in a little bit more time. And we're also going to create our own pressure enthalpy diagram from measured points along the system, just using pressure and temperature readings. Then I want to talk about the setup and procedure, sort of what the apparatus is, how we'll go about performing the experiment, and also some of the equations we'll use for the calculations, and a sample calculation of the coefficient of performance. And that's a fridge, just for reference. So the refrigeration cycle is kind of it's very related to one of the first things learned in thermodynamics, which is a heat pump. So the way a heat pump works is by putting work into a system, you're able to take heat from a high temperature area and expel it off into a low temperature medium, sort of pump heat there. And a refrigeration cycle kind of works a little bit backwards. So your goal is to pull heat out of a low temperature medium and expel it into some higher temperature area, which doesn't really happen in nature, which is why you need to have a refrigeration cycle to do that. So for the experiment, we're going to use R134A as our refrigerant. There's other refrigerants you can use like R12 and things like that. And this is known as a vapor compression cycle because the compressor only compresses vapor. So the four main components you have are the compressor, the condenser, the expansion valve, and the evaporator. So we'll start the cycle at the compressor, where you have a high pressure, high temperature vapor that comes out. It's sort of superheated before it goes into the condenser, where it has the job of trying to expel all the heat from the system. And in doing this, it causes the vapor to condense. So now you have a high pressure, high temperature liquid that comes out before going to the expansion valve, where the expansion valve sort of drives it gets the refrigerant to the lowest point in the system, lowest temperature, before going to the evaporator. And it does this by expelling most of the pressure, sort of purging it. And in doing so, your temperature drops really far as well because of the pressure-temperature relation. So it then goes to the evaporator, where you have the lowest temperature in the system, which drives the heat transfer from your refrigerator, which is already cold, and you want to get it even colder. So then it evaporates, and you have a low pressure, low temperature vapor, and the cycle repeats. So the coefficient of performance is a sort of measure for comparing your output of the system to the input, or your desired output rather. It's not the same as efficiency, because efficiency can't really be greater than 1, so that's why they came up with the coefficient of performance. So to measure the coefficient of performance, or COP, for a cooling system, you can look at your heat transfer, your driving, and how much work it takes to do that. And for an ideal system, like sort of a Carnot cycle, you can look at just the difference in temperatures and calculate it that way. COPs for commercial refrigeration products are usually between 2 and 3. They're usually always greater than 1. So these are some of the diagrams. I don't really have much time to explain them, but yeah, you have pressure, volume, temperature, entropy, and pressure enthalpy. These are not really related, but they're all for refrigeration cycles. So the experiment goals, like I touched on in the beginning, is that we're going to experimentally determine the COP and also compare it to a theoretical value. That'll be the first procedure. And the second one is to take temperature and pressure measurements along the entire system and then create our own pressure enthalpy diagram and compare it to an ideal one. And that's the one given in the handout for R134A. So the setup looks just like Mr. Lee showed us. So we have in blue the water circuit, which we'll be able to control with the pumps, which is what's going to go through the two heat exchangers, the condenser and evaporator. And in orange, we have the refrigeration circuit, where we can measure the pressure and temperature at pretty much any point before and after every component in the system. So for the procedure, we will determine the COP of, I guess, the condenser. We'll set the flow rate of the water to 5 liters a minute and the compressor to 40% and let the system stabilize before taking temperature measurements of the water before and after the condenser, the flow rate and power consumption measurements, of which we'll be able to calculate the COP. And then for the pressure enthalpy diagram, we'll vary the flow rate and take temperature and pressure measurements of the refrigerant around the system. These are some of the equations, like for heat and enthalpy, a lot of it is kind of related. For the COP, I'm using, for the next calculation, I'm using the equation I showed in the beginning. So because we haven't done the experiment, I haven't taken any measurements, I just came up with some differential pressure and some work that we put into it. And then for a given flow rate and CP of the water, we can calculate the mass flow rate and then the heat flow that goes through it, and then calculate the COP, which I got is 2.1, but those are just kind of random numbers. But yeah, that's it. You have any questions?
Any question from? Okay, here's my question. Can water be used as a refrigerant?
No,
Why?
because of its density. It's a sort of like its energy density, or because of its thermal properties.
Which of the properties are we actually interested in? Like why
Specific
can't we use any liquid as a refrigerant? What are the properties of liquid that make them very good to refrigerate?
Freezing point.
Hmm?
Freezing point.
Okay, it's fast.
You also have a compressor, right?
Well, freezing
Yeah.
point is fast actually. But there's like the key factor actually that makes a liquid, part of the key factor that makes a liquid a good refrigerant is the boiling point. The boiling point. The boiling point of water is what? 100 degrees Celsius. It simply means there is no way you can actually, if water is to evaporate and cause cooling, it has to evaporate at 100 degrees Celsius, right? And that temperature is very, very high. But if you look at these refrigerants, they actually boil at very, very low temperature. Very, very low temperature. And it is because of that low temperature that they can exchange heat with anything you put inside the refrigerator, and then cooling happens. So just take note of that. The refrigerant should have very, very low boiling points. That's it. So that's all right. Next group leader.